The previous class we discussed about the uh, Lagrangian equation from the Hamiltonian principle. So this is the Lagrangian equation from the Hamiltonian principle derivation. Now I would like to discuss about generalized momentum and cyclic coordinates. Okay, let us consider a single particle moving with velocity along x-axis. The kinetic energy of the particle is a single particle moving with velocity x dot along x-axis. The kinetic energy of the particle is T equal to 1 divided by 2m x dot square. This is equation number 1. The derivative of t with respect to x dot is given by the function. The derivative of this kinetic energy T with respect to x dot, that means partial derivative of T, partial derivative of x dot equal to m x dot. Okay, 2 gets cancelled, remain 1 m x dot. So this is nothing but momentum P. It defines the momentum. If v is not a function of velocity, I mean potential energy is not a function of velocity, that means v equal to v of x, right? And we can write dv divided by dx dot equal to 0. Then the momentum P can be written as P equal to this function. I'm going to write partial derivative of velocity t minus v, or we know Lagrangian L equal to t minus v. So this is equation number 2, because L equal to t minus v. Similarly, for a system described by a set of generalized coordinates, I mean q's, and generalized velocities q dots, then the definite generalized momentum corresponding to the generalized coordinates q's, we may written like this: p q equal to partial derivative of L divided by qk dot. This is equation number 3. This is called as conjugate momentum or canonical momentum. So should write down here the note. Similarly, for a system described by a set of generalized coordinates, we know those are the q's, and generalized momentum, sorry, generalized velocities q dot case, then the definite, the generalized momentum corresponding to the generalized coordinates q case as p, momentum p equal to partial derivative of L divided by partial derivative of velocity. So this equation we call the conjugate momentum So here the conjugate to the coordinates q's. Okay. For more clarity, I'm going to write this one: conjugate to the coordinates q case, okay, or canonical momentum. this equation called as a conjugate momentum or canonical momentum. For conservative system, the Lagrangian equation for conservative systems, the Lagrangian equation is d by dt partial derivative of L dq dot minus partial derivative of L divided by generalized for net equal to 0. This is equation number 4. Now substitute equation number 3, this one, equation number 3 in equation number 4. Substitute equation number 3 in equation number 4. We'll get d by dt in place of partial derivative of L divided by partial derivative of velocity is nothing but momentum. I mean conjugate momentum or canonical momentum of the system. Dou L divided by dou Q equal to 0. So this we are going to write P dot, right? This one P dot equal to partial derivative of L divided by dou Q. Now the expression for Lagrangian L of a system, certain coordinates qk does not appear explicitly, then it's better to write these words here. Now the expression for Lagrangian L of a system, a certain coordinates that means q case does not appear explicitly, then partial derivative of L divided by partial derivative of qk equal to 0. That means pk dot equal to d by dt partial derivative of L divided by qk dot equal to 0. This is not 60, okay? Hence the integrating on both sides this equation will get pk equal to dou L divided by dou q k dot equal to constant. So and hence integrating on both sides above equation. So P equal to constant, right? Final equation we got this P equal to the constant. Momentum equal to constant. Thus, whenever the Lagrangian function does not containing a coordinates, especially generalized coordinates explicitly, the generalized momentum p is constant of motion. The coordinate qk called cyclic coordinate. So I'm going to conclude this one here. Those whenever the Lagrangian function does not contain a coordinate especially generalized coordinate explicitly, the generalized momentum pk is a constant of motion the coordinate qk is called cyclic coordinate. Or ignorable. Okay, so this is the generalized momentum and cyclic coordinate.